Hey guys, Dr. B here. This is topic 5.5 collision model. The objective of this lesson is to explain the relationship between the rate of an elementary reaction and the frequency and energy and orientation of molecular collisions. Collision theory. Collision theory explains why different reactions occur at different rates. So what's happening for a reaction to occur, period, is that particles need to collide all the time. However, not every collision has enough, so to speak, to result in the reaction. So a reaction occurs when bonds are broken or remade. I'm sorry. In order for a reaction to occur, according to collision theory, you need three things to occur. Particles must collide, obviously. The rate of the reaction is dependent on how frequent this happens. They must have sufficient energy. This is known as the activation energy. Okay? They also must have the correct orientation. Certain parts of one molecule and certain parts of another must meet in order for the reaction to actually occur. Okay? So collisions. So they occur all the time, but not all of them result in a reaction like I kind of had mentioned before. The way to think about it is it helps us to think about these collisions occurring because the chance of two molecules colliding is high if they're bimolecular. However, if there are ones that are not bimolecular, that means it takes more. There's not a higher chance for them to collide themselves. So when I say bimolecular, means two molecules are involved. If it's tri or termolecular, that means that there's more molecules involved that are probably not going to happen most likely. So if there are more than two molecules involved, most likely multiple reactions need to occur for it to go. Okay, sorry, activation energy is the minimum amount of energy that is needed for reacting particles to kind of do the reaction. If there's not enough colliding particles or the minimum energy is not reached, it will not happen. This energy is used to break bonds. Where are we at? Sorry. So we talked about the Maxwell-Boltzmann distribution. So if we increase the temperature, we can kind of increase the kinetic energy. So we saw the relationship that kinetic energy and the temperature, they're correlated. So if I increase the temperature, I increase the average kinetic energy, all that type of stuff. So on the Maxwell-Boltzmann distribution curve, the energy activation is labeled EA. This represents the minimum energy needed for a successful reaction to occur. The particles with energy greater than the activation energy have enough energy to react, while the particles that have a lower amount ain't going to happen. Okay? That's the way to describe it. It ain't going to happen. In order to increase the number of particles with energy greater than the reaction, one must heat the sample. So remember we said increase kinetic energy, increase the temperature. We are increasing the level. We're going to not increase the activation energy. We're just increasing the amount of energy of the particles. And if that surpasses the activation energy, the reaction will go. So like I said, the activation energy is not increased. It's just that more particles have a chance to surpass that. So notice how in the graph shown that the activation energy does not change. Notice if we if we increase the temperature, the particles are more spread out on the Maxwell-Boltzmann distribution curve, to where some of it is actually skewed towards the activation energy. The lower the temperature, the more molecules that are not going to hit that particular level. Therefore, it's not going to go. Like I said, orientation of the particles. This is essential for reactions to occur because it needs to be hit at the right angle, the right part, break at the right part, etc., for it to actually to occur itself. Specific orientations are needed for the particles to the specific orientation is needed for the particle to collide and for it to actually do what it needs to do. If there is no, if the orientation is incorrect, meaning it's going to hit at a certain point that's not going to cause a reaction to occur, then it's not going to happen. Given the following reaction, which set of reaction conditions will result in the highest reaction rate? Explain in terms of collision theory. So I have experiment 1, 2, and 3, certain number of moles of each. The temperature is all the same, if you notice that. So temperature has no effect on this. So if you'll notice, we have a concentration, we have a certain amount of moles for each of our reactants, and a certain volume. You'll notice that the volume changes, and the number of moles in reaction 1 and 3, they're the same. So maybe that'd be a good idea to look there. So you'll kind of notice that in comparison, you remember moles per volume, that's a good ratio, good thing to focus on when you're trying to figure out which one's going to happen. So it's asking you to explain in terms of collision theory. So we have to talk about that. So there are more moles in number 2, and the volume is greater. If you have an increased volume, that means increased volume, less chance of particles to interact. So probably not that one. Now let's look at experiment 1 and 3. Experiment 1 and 3 both have 1 mole of each reactant, but the volume increases in experiment 1. So if you increase the volume of your container, that means there's going to be less pressure. Less pressure means that they're less likely to interact with each other, the particles. So experiment 3 is the one with the highest reaction rate. In comparison, the concentration of the particles in experiment 3 is the highest. Therefore, particles are more likely to collide with each other. The graph below shows a Maxwell-Boltzmann distribution for reaction at 3 different temperatures. On the first graph, add a line that indicates a low activation energy. On the second graph, add a line that shows a high one. Explain why you don't see a large increase to the reaction rate when the temperatures increase if the energy activation is low. All right, so for something to have a low activation rate, that activation energy, wow. That means that put it this way. So the activation energy, it's a kind of a correlation, or it demonstrates that if it's a low energy, the reaction will not take a lot of time for it to get there. So that's what I'm trying to say. So the speed, if you will, speed of the molecules, for it to be a low activation energy, the speed doesn't have to be that high. So for letter A, do a different color. Letter A, let's just say our low activation energy is over here. For letter B, a high activation rate, that means it takes more, the particles need to be moving faster for it to do that. Oops. Explain why you don't see a large increase to the reaction rate when the temperature is increased if the activation is low. So why is it that if it's the reaction rate doesn't really, why you don't see a large increase to the reaction rate when the temperature is increased if the activation energy is low? So focusing on the first one, why is it that it's notice that the one that's the temperature is high and the energy activation is right here, why is it that the reaction rate is not increased? So this is letter C. Oops, I'll do a different color you can see. Letter C. Because the majority of the particles have energy greater than the activation energy. Oh boy, running out of space. If the activation energy is low, you don't see a large increase of reaction rate need more space because most of the particles can already react and have a chance, I'm just going to say this part, have a chance of having a successful reaction occurring already. So essentially, why does it you don't see a fast or increased rate? It's because you already surpassed the energy activation for most of the particles. Therefore, the reaction rate doesn't increase because it's probably already done, essentially. All right, guys. So if you have any questions, please let me know. Thanks.